Hey everybody, so this talk is going to be a merged version of two talks. One is what I've been giving on our work to build Olmo 3 as a thinking model, and then I've also given a talk at NeurIPS on our approach to evaluation for post-training in Olmo 3. So this is a mega talk with everything in one. Bear with me, it'll be on the longer side, but I think the material is pretty great, and people will really enjoy kind of this top to bottom picture of some perspectives on everything that goes into building a frontier model. So I'm going to get into it. It starts with some very nerdy stuff and then kind of will be more approachable throughout, on and off. So if you look at the landscape of open models, the first thing that I need to convince you of if I'm introducing Olmo 3 Think is why we need another thinking model. 2025 has been the year when everybody has released a thinking model. It's organizationally needed because it is a platform for doing far more interesting research in models. These reasoning models let us do amazing things on harder benchmarks with agents and everything. So we need a lot of them. And what we're seeing is that a lot of the models from industry actually have a lot of kind of common strengths and flaws. So we've seen a couple papers from academia, and honestly more at this point since I've made this talk, that are showing ways that this latest type of reinforcement learning and reasoning research in the open is really messy. So one of the papers, Spurious Rewards, is one that I'm on, where we showed that some of the Quen models actually will improve in performance if you train them with RL on literally random rewards. This isn't a method, it's an empirical paper that's pretty much saying that something is wrong with the base models in our method of evaluating these RL algorithms. And this was corroborated later with a bit more spicy title where they're saying that Quen might have some data contamination issues in pre-training. So what we need to see is, like, can we do RL research where there is not any contamination in the base model and we can trust all of our results? Because this RLVR, this reinforcement learning from verifiable rewards, these reasoning models are going to be a fundamental area of study for many years in the future. So we need a clear base by which the research community can understand the results. Specifically, to zoom in on this paper on the right, the Spurious Rewards, it's fun to talk about why it'll work because it's a kind of interesting hypothesis on the interaction between data and algorithms. So what we see here is that on the right, if you ask the Quen 2.5 math base models a math question, which is something very close to the evaluation Hendrix math, where you just change the numbers, the model will do some hallucinating tool integrated reasoning. So it'll say that it's going to run code, which it can't actually run, and then it'll generate an answer to very high precision. What this makes us think is that the model has been trained on a lot of tool integrated reasoning data in the base model, regardless of what's going to come at post-training. So when you're training on RL later, the model could be doing things like this to further refine its behaviors on common benchmarks like math. So what is happening in RL algorithms is that the exploration of the model, and especially with these reasoning models where we're trying to see the sequence length increase, can be hinged on some really low probability tokens and the model actually changing its behavior. In the DAPO paper, there's actually a hypothesis that certain types of clipping in the algorithm, the clipping is core to these PPO style algorithms where they're restricting the gradient updates to a trust region, can actually make it so the model can explore less, suppressing these kind of low probability tokens. And the opposite of suppressing low probability tokens is increasing high probability tokens. And if the model was trained on a lot of things close to the test set, that could be the most common behavior for the model. And training on these spurious rewards might be kind of pulling this behavior out, where the model is learning to behave really close to this test set and the evaluation scores go up, even if the model isn't actually changing fundamentally at all. This is only a hypothesis, but it's a cool intuition that you can revisit as you kind of spend more time trying to understand how these latest RL algorithms are working and they might interact with the base model. But really at the end of the day, we just need cleaner base models so we can move these sorts of things away from hypothesis and into actually established study. And this is the idea with Olmo thinking. Obviously, any Olmo model has a lot of goals, where the goal is to make great fully open models that you can use for a lot of tasks. But this kind of reinforcement learning study was a large motivation that we revisited throughout as this process is going for months and months and months. In this talk, we're going to go through each of these kind of stages so that we can abstract the training of Olmo 3 and Olmo 3 thinking into these 6 stages across both pre-training and post-training. And we're going to do each of these. But first, kind of something we're talking about with these stages is that Olmo is a model flow, which means that you can kind of take this post-training recipe that we're presenting and modify it to its own use cases. For example, you could change pre-training earlier on, such as before long context if you have a lot of data to fit your specific needs, or a post-training recipe is staged with intermediate checkpoints. So you might be able to find a checkpoint that you actually think is better for your use case and just fork it right there and apply our stuff later on top. We use this sort of idea to create many variants of post-training. So we have the instruct model, which is very quick thinking. We have this reasoning model that I've been talking about, which excels on hard tasks. And we also have started working on reinforcement learning from the base model, which is kind of a foundation of distant recipes where it's much more RL heavy rather than using this strong supervised fine-tuning stage to instill specific behaviors in the model. We plan on adding more recipes to this and really hope that people can kind of modify Olmo 3 based on us releasing everything as we have, and especially now that Olmo 3 is a bit more capable of a model. So wherever we start with a model, it all starts with architecture. I think that it's easy for post-training people to kind of ignore this, and it makes for operational kind of cleanliness where having your post-training and pre-training teams talking all the time actually can be really hard. But there are certain things that you need to get right at pre-training, especially as your post-training is shifting towards a more reinforcement learning heavy stack and something with much more inference. So if you look at what we're doing, our Olmo 7B particular and our Olmo models of Olmo 3 have been really close in architecture to Qwen 2.5. And you can compare this in terms of the context length and therefore the amount of training time it takes when you're looking at these kind of RL updates. So here we're baselining the performance of our architecture versus others when we would be doing the last stage, which is this reinforcement learning post-training stage, which can be most sensitive to this architecture because pre-training obviously is taking this into account. So we can take a random RL checkpoint during training and compare the architecture's training time. And here, in terms of the actual RL policy gradient updates, it's pretty close. But when we look at different metrics, such as GPUs needed to run inference, you can see that the Olmo model just needs way more GPUs, and you can translate this into cost, which is insane, where the cost is way higher in GPU hours to actually do this inference or the whole RL stage overall. And this is because the 7B model doesn't have this innovation called GQA, Group Query Attention, which is a huge memory saver. So what we see as my slides change is group query attention essentially shares some of the weight values across different parts in the forward pass. And this can save about like 80% in memory of the attention heads. And this is a huge factor in post-training in terms of inference and GPU efficiency and experimental efficiency, where it's like now we know that every future model needs this. Our 32B, our bigger model has this, and it's just kind of one of the things that you can learn along the way. So you can get this plot where it's like in terms of our RL experimentation, the 32B model we trained, because it has GQA, even though it has over 4 times the number of parameters, is actually not that different in terms of the GPUs we need for overall RL training. We can scale up the 32B training a bit better with different parallelisms, but like in this case, it's just like the 7B model we need to retrain as soon as we can, and we know this. But these are the types of things that a lot of post-training researchers won't talk about. So if you do like a GPU hour comparison between Olmo and Qwen, therefore like training on Qwen is going to be much more efficient, and that's a big factor when you're just running hundreds of experiments over time to push the frontiers of what is happening algorithmically. Okay, so that's the architecture things. The rest of pre-training, we're going to talk about how we choose data for a bit. The biggest story for all the data on pre-training, I would say, is a readjustment of the prioritization of pre-training much more heavily on reasoning. So we knew that we wanted better math. We knew that we wanted better code. And for any pre-training process, there's really 2 things you need to do. 1, you need to get more data, that is sourcing. And then 2, you need to get the best data out of those sources. And then I guess a 3rd step, and then you mix it all together to find your optimal mix. And what this looks like is that There's a lot of actually great methodology for choosing pre-training data, especially when you compare it to the Wild West of post-training. So what you can do is you could take all of your sub-sources that you're considering using in your final mix, and you can train a bunch of tiny models on them, and you can see the correlation between these tiny 30 million parameter models and the downstream loss that you're training on. And you kind of get these and you take a huge sweep and burn a lot of compute over all the data you're considering. And then with your evaluation set, you can just fit a regression which tells you what are the best subsources in your data, and then you get the final mix by kind of pulling this all together. And it's really elegant, and it's this thing that we use for pre-training and mid-training, and it's what allowed us to kind of really trust what we're doing and just get the best data mix. I think that this type of thing is a really elegant part of language modeling where so much can kind of feel like vibes and YOLO runs. And therefore we get our new mix, which is much more reasoning focused. Another thing that we needed to do in order to do a reasoning model at all is do this long context extension. Previous Olmo models only had a max context length of input and output of up to 4K tokens. And if you want to do reasoning on hard problems, you need to be able to spend upwards of like 30K tokens thinking on an answer. So we knew that we and nobody in the community would be able to do reasoning research on Olmo models unless we solved long context. And long context, like many things, can be solved in many ways. In the case of Olmo, we found it to be mostly architecturally limited. I think Luca gave me this hilarious quote where Luca is one of our data leads, and Luca was like, I hate long context because for long context data doesn't matter. I think it's a bit of an oversimplification, but it is all comes down between the intersection of compute, how much you are spending, your data quality, and your architecture. And with AI2, we tend to be fairly limited on compute, and our data flywheels were just getting started. So we had a smaller, high-quality data set where architecture was a huge limiting factor. What you can see on the right here is 5 different Olmo architectures tweaking things like QK norm or whatever, and on the same long context data set, there could be a huge variation in long context performance. In talking to more people about this, it's fairly established that you can improve your long context numbers even if the architecture is imperfect by putting more flops into it. And this could be why there's a lot of variation in how people choose architectures in long context about industry. But at the end of the day, in terms of basic tests like having long context, you just need to have it if you want people to do RL research on your model, and it's a must-have and something that we'll invest more energy in going forward. I think that shouldn't be surprising at all. Okay, from here we're going to go into what is like the core bread and butter of what I work on. I've been a post-training researcher and lead for a while, so it shouldn't be surprising that most of this talk is going to be on post-training. When you think about the current Olmo 3 recipe, you should really think of it as being optimized for small models. This is a distillation recipe where we're taking the strengths of DeepSeek and Quen and we are instilling it into small models. This is very different than frontier model recipes where they start with RL, they do this cold start and very scaled RL reasoning to begin with to get these dynamic behaviors. That DeepSeek R1 style recipe is something that's very on my mind. I kind of want to rebuild our whole post-training scratch from scratch next year in order to have that RL focused recipe, which works on bigger models rather than the small one. But at the same time, a lot of people are going to benefit from this recipe because a lot of people train small models, and we're showing fairly straightforward interventions in order to improve the performance of your small models. There's a lot of low-hanging fruit here. So the foundation is always going to be, so you can see this 3-stage recipe is similar to our 2-3, where we go to SFT, DPO, preference learning, and RL. These stages we have found they just all give strong performance gains, but the foundation is in SFT, which is also like fairly straightforward. You just need high quality data. So what we did, it's a big mixed bag of things that shouldn't be super surprising. I think we took strong teacher models. We used a mix of QW-Q32B and DeepSeek R1. We use a lot of filtering. We use existing open data sets such as OpenThoughts 3 we took extensively, and then Prime Intellect Synthetic 2. For OpenThoughts 3, one of the huge gains that we have was the original data set was 16K length and had a lot of truncated samples. When we saw the truncated samples in it, we thought, let's just extend it. And we extended it to 32K length. We trained with SFT in a longer context, and the performance went up a lot. At the same time, a lot of early models released for reasoning really were unstable when it came to chat or instruction following. So a big focus of our work was to kind of improve the robustness across more domains of open reasoning data, including things like safety, kind of just general tasks, chat, and so on. And like this really worked. You can see the data set on the right. It's a couple million prompts. It ends up being in token count because these are long contexts, about like 20 times the tokens of our old SFT data sets like Tulu3 or Olmo 2 SFT. And that's just because of the thinking tokens. So it's really a lot more flops that we're putting into the model to do SFT, but it does a job. It's straightforward gains. I think that you can look at our filtering. There's a lot of steps. There's a lot more that can be done on data quality. The lore for this is that I made a lot of this data set in a weekend because we had a ton of cloud credits that were expiring, and I was generating billions of tokens from DeepSeek in order to make this work. So shout out to Azure AI Foundry and Nair who gave us the resources for that. But like filtering is what you would expect. I think that we take a lot of care at AI2 to remove non-commercial prompts and other data sources that have licenses that'll make it harder for anyone to adopt our work. We used a lot of chat data, but chat data in the wild, for example, Wild Chat is a project where they just let people use ChatGPT and then log the data with when you have them agree to certain terms. And like general chat data will have a lot of random stuff, like create an image of X. Like if we're training a text-only model, we don't need multimodal inputs, and it just kind of is wasting tokens and potentially destabilizing the model. Also, a lot of open reasoning data has kind of just broken things where it's known that for a reasoning model, you often have these like think tokens and then end think. A lot of open data will just be missing end think or missing think. So we just remove the data with basic formatting errors so the model doesn't get confused by that. We do some domain-specific filtering, which is for safety. We want to make sure that the style of answers and refusals for the model is accurate. We have a lot more work to do here, but there's, for example, like DeepSeek particularly likes to randomly talk about how it's an AI model that should follow Chinese socialist values, and we didn't want that model to say that at all, so we spent a lot of time removing that. Also, identity filters are really hard. The models love to say in their answers, like, I'm a DeepSeek built by blah, 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 or I am Quen. And we took a lot of work to try to remove this because there are millions of mentions of various model makers. And we are honestly we need to do more work on this. And it's very easy to have your model think that it is made by somebody else. And you have to spend a good amount of time on data curation to make sure your model knows who it is. Number 6, repetition filters for open reasoning models, for whatever reason, compared to the closed ones where you don't have the reasoning trace, are much more unstable. I describe it about 0.01% or even more. So like 1 in 1,000 and 1 in 10,000 samples from Quen have a total mental break where the model will just repeat paragraphs like 50 or 100 times. And what is remarkable is that the model often recovers from this. So it'll be in a doom loop for thousands of tokens, tens of thousands of tokens even, and then it'll recover and sometimes give a right answer. But this repetition of tokens feels very risky from a loss perspective, and it's worth removing a few samples from everything. All in, we only remove a few percent from every data sets that we make, but these seem like really low-hanging fruit in terms of improving the stability of the model and models that people train our data, or models that people use our data for in the future. When we're actually building this data set, the TLDR is that we ended up making a lot of data, and pretty much we ended up just using all of the data once it was filtered. Along the way, we were trying to do a lot of ablations to see if different data sets were obviously better or worse. And the way that we did this, which is you'll see easily reflecting on the mid-training methodology I told you, that it's much more YOLO. But we took a base mix of about 100,000 samples from OpenThoughts 3, which we made and filtered. And then we tried adding a whole bunch of other chat and code domains to it because we wanted to make sure that we could add broader domains to the model without degrading the performance from our kind of core math code STEM mix, which OpenThoughts 3 was. And pretty much all of these work. The models are very good at identifying the domains and then kind of separating them. So adding different domains of data, even with reasoning, works fairly well. And you can see much more of this in the paper. Okay, on to DPO. This is one of the most surprising things from the paper for me. I think that DPO is very much this direct preference optimization is frowned upon colloquially in communities right now, where people just don't want to use it. We found it to be incredible low-hanging fruit and one of the easiest things to get off the ground for our models in return for performance. So if you look at RLHF and preference learning, generally what you're doing is you're solving an optimization where you have some reward, which is based on labels of preferences between two answers, and then a constraint, which is the distance constraint on the model. This is what it looks like. DPO is derived where if you analytically derive the optimal solution to this problem, DPO is what you get, and therefore you can just use gradient ascent on the reward maximization problem. We've been using this for years. It's a great baseline. I think a lot of criticisms will be describing that as not aesthetically pleasing, but in practice you can get such good performance with way less engineering effort that it's hard to divert the engineers away from much more compelling and kind of 0 to 1 style problems, which are like the RL infrastructure for verifiable rewards, where if you don't have engineers there, you can't do it. Where applying engineers to improve on your RLHF stack as a substitute for DPO, you don't really need to do because DPO is largely fine. Previously, the gold standard for DPO, something that we use for Tulu 2, Tulu 3, Olmo 2, Tulu 2.5, is this ultra feedback data set, where the core idea is that you have a good set of prompts and then you get to take a diverse selection of models for the completions and then use LM as a judge with a rubric effectively to create this binarized data with a chosen as a stronger and a rejected weaker response. This is built on the idea of a model pool, but there's a critical flaw now where as our prompts aren't really changing that dynamically, most of the open models out there actually are saturating in performance where most of the responses are similar. So the delta between chosen and rejected answers you get when using ultra feedback is actually quite low. And this was the core intuition behind the paper that inspired our DPO work, which is the delta learning hypothesis by Scott Gang. And the idea is that in DPO and preference learning, it's the contrast between the pair of chosen and rejected answers rather than the quality of the chosen that impacts the learning signal for your model. And what we used is we ended up using two Quen models where the reasoning models of 32B as the chosen and 0.6B as the rejected had a really nice consistent delta in their answers. And this gave the model a really strong signal to learn from. Fun fact, as we were writing up the paper, when we were in that small LM actually used these two chosen rejected models as well. So they arrived on the same implementation, even though they probably hadn't read or gone through the whole effort that this paper that Scott did, and Scott was one of the core authors on Olmo 3 post-training as well. So when you look at the data that we use in terms of prompts, the prompts look very similar to the reasoning SFT. They're a bit more close to the kind of Tulu 3 and Olmo 2 prompt pool, but there's a lot of overlap between SFT, and this just gives us a nice diversity, and it's good to have some new things. I think we could innovate on this a lot more, but it's largely unsurprising is what I would say. But in terms of the performance, what you should be looking at here is the left three columns are the performance of our 32B think model. First column is SFT, which I talked about earlier. Second column is DPO, which shows you the gains with this simple delta learning approach. And third is the released RL model. As you see, we can gain about 2 points on average, especially in some very hard domains like AMY and coding, where DPO is just really helping. And intuition that I have is that DPO is helping the model learn the useful modes for reasoning and kind of making its reasoning skills a bit more robust as it's learned from this contrast between good and bad reasoning with this stronger 32B model. For comparison, DPO runs and evaluations take about a day. We're gaining a similar bit about a performance or a bit more with RL can take weeks. We've also been studying regularly, but not definitively, that doing RL on top of DPO is kind of stacked gains. And whenever we revisit it, the models that we trained with RL, if we were to just skip DPO, tend to be worse. So we're checking to see if we're just eating from the RL performance later by doing DPO, and we haven't seen that the case. The DPO seems like low-hanging fruit that was worth doing and kind of just really helps us take the next step in terms of model performance. So we've talked about most things here. I think we talked about pre-training to get to the Olmo 3 base model. We talked about SFT and DPO to get a really strong foundation of reasoning based on distillation from strong teachers. But the most important, like the most intellectually interesting thing about training Olmo 3 Think is like this reinforced learning from verifiable rewards phase, this RLVR, which everybody is talking about, which is like how much performance improvement can we actually get from RL? Like, is it just learning formatting? And like, what do we need to do RL on these really long context models where they generate tens of thousands of tokens per answer? The key thing here is that it was a very challenging infrastructure problem, and most of the time was spent with a few, maybe 3 to 4 excellent engineers and researchers just building this infrastructure, and that was like their entire summer, and then we got to reap the rewards of it. I've used this diagram multiple times. This is the basic introduction to reinforcement learning with verifiable rewards, where you start with the training data, which is prompts. The policy that you're learning and updating over time generates completions. Those are the actions in the RL sense. And these completions are graded by some sort of Python program, which says whether or not that completion was correct or partially correct. And that is used for your RL update. I think that I reiterate multiple times that this is very hard. Do not take this lightly. If you do not have multiple engineers doing this full time, you should very likely not be spending your time building something from scratch, and you should use something off the shelf. When you look at Olmo RL, this is what we called our kind of approach, which builds on a lot of prior work. We're using a lot of things from the literature, and then we retested them to make sure that they work together. A lot of papers will propose one idea, and when you take a bunch of ideas individually, you don't know if they will work together. I think some of this is not super surprising. We've highlighted active sampling because that's kind of a new infrastructure approach that we added that just lets our training be a bit more efficient in time and how we spend GPUs. So the first one here is zero gradient signal filtering. Essentially, in GRPO, when you have these groups with multiple answers per prompt, if all the answers are the same, then the advantage becomes 0, and that doesn't do anything for the policy. This effectively reduces the batch size, but makes us so we don't have to compute gradients on something that has no signal. Active sampling I'll talk about, which is a way to make sure we have full batches. Token level loss, which helps with length bias with the implementation. We don't use a KL penalty, as many people haven't. We took clip higher from DAPO, which is a way to encourage a bit higher exploration. We use truncated importance sampling to mitigate the log probability difference from Hugging Face, which is where our training steps are, and VLM, where we're doing our inference for our rollouts. And we don't need the standard deviation normalization, which I think is from Dr. GRPO. I think we experimented a lot of other things, such as overlong filtering, but the ones we chose were very stable. So we took a conservative approach here to try to find a stable recipe that we could launch for long training runs to get full performance. This shouldn't be super surprising, and we'll surely keep iterating this over time and share how our RL stack and approach is changing. If you actually look at a GRPO style loss below, you can see that I highlighted a few things color-wise to show where they are mapped to the GRPO loss function. So the kind of truncated importance sampling reweights the advantage based on the probability delta between the generator and the trainer. And then you can see the advantage calculation is a bit changed. And this is pretty standard stuff. I think looking at the paper and the references is the best place to go deeper. So now that we have this, I think it's kind of like, how do we actually translate this into infrastructure where we can put a lot of flops into the model at this reinforced learning stage? I think what it ends up looking like is you have a learner, which is where the reinforcement learning updates are happening, which is on much fewer GPUs. And that learner is given a set of prompts, like it controls which prompts are going to be generated, and those prompts are dispatched to many different actors, which are many different generation GPUs, because generating long completions is the bottleneck empirically. So we need to spend a lot more GPUs on inference than on training. As these generations come in, the results are sent back to a separate queue, which makes the batches to pass to the learner, which takes the RL updates. And every so often after these RL steps, the weights are synced to the learning GPUs. And we'll say more about when and why that is important. So if you look at kind of naive on policy RL, I talked about 2 sets of GPUs. One is the generation GPUs and one is the training GPUs. Generation GPUs are generating long completions to prompts. This is done in VLM. And the training GPUs are calculating the verifiable reward to understand if the completions were right. And then they're training with Hugging Face transformers. This is just a gradient step. Naively, there's a lot of problems with this because these two GPUs, you could do them on one GPU and go back and forth. That's very slow because spinning up VLM is slow. But what happens is that you actually have a bunch of idle GPUs where your generation would stop and your training would stop in alternating fashion with the most basic approach. So the core idea for RL training is mitigating idle time while maximizing performance. So what we can do to start with is that we can continuously run the GPUs. What we're going to see here is that it turns out that our data is now off policy. In RL derivations, one of the core assumptions is that your actions are sampled from the current policy when you're taking gradient steps. In practice, there's some softness here where you don't need it, so we can just continuously generate, and then we could update our RL policy with like 1 step old data so that our generation GPUs never need to be idle. Empirically, this is a pretty minor change and more kind of risky changes in terms of going more off policy, where we're drifting more into the unknown of kind of what is empirically possible in RL to gain more and more speed. And this is a balance that you'll see me revisit. And because we're doing this, we also have to, or in doing this, we also see a mismatch between VLM, which we're generating the completions for, and the trainer. Essentially, we need to use VLM because it's so much faster than something like Hugging Face, but the kernels and things are slightly different. So the log probabilities are what we use in this RL loss, end up being slightly different, and that adds numerical instability. So what we can do to solve this is we have the log probs, but they're for VLM, but they're incorrect, and we could just get them again in transformers, and this is kind of gap. And ideally these would be identical, but that's very hard to implement. So we tried to just change things in VLM to make the log probs exactly right. That didn't really work. That is a huge time sink. Some people might be able to do this. The thing that you can do to get around this is you generate your tokens in VLM, you can pass the tokens back to your trainer, and then generate the log probs. It's slow because you have to do another inference pass, but you actually can get the match. This ends up being slower, and the thing that people actually use the most is something called importance sampling, where you compute the probability ratio between your learner, which is the Hugging Face, and your VLM, which is the generation. And this ends up being the right way to, or a way to kind of correct this probability mismatch in a really efficient manner because you have all of this information already. I'm just checking in on Phoebe in the background. There you are. So if we're back to this, we know that this actually isn't really realistic. What's happening in practice is that we have a very big long tail of generations where the longest sequences, where the model thinks the most, can be a huge bottleneck on the GPUs. So the thing that isn't realistic is the fast transition between all the gen GPUs being active to all the trained GPUs being active. And what happens is we're spending a lot of time on generation. And in particular, we're spending a lot of time on generation because one sample is way longer and is the bottleneck. So something we have to figure out is like, we don't want to wait for this one sample because A, our training speed will be lower, and B, our utilization is crashing. So what happens is we want to figure out a way to make it look like this top row where we're continuously generating completions and continuously taking training steps on the bottom. We just wait for enough completions in order to take our training step. And the idea is like, how do we deal with this one point, which some of the tokens in the first part of this completion are going to be multiple steps off policy by the time it goes into the learning update. And what we do is that as the new RL updates happen, so these dotted lines are the RL updates, we just update the weights while the model is generating. So the model is generating a really long completion to a math problem, and we literally just change the weights of the model when it is completing, and this ends up being it numerically sounds weird, but in practice it ends up being okay, and it's a huge speed improvement. So this ends up being like a 4x speed up doing this in-flight, what we call in-flight updates, where we're just continuously updating the model. The library from ServiceNow, Pipeline RL, tends to be the canonical reference academically for this because they were the first ones to open source code with this. But this in-flight updates is a core implementation used in many libraries, but actually not all the open source libraries have it. So make sure you check if you're taking an off-the-shelf library to do RL. Still, there's things that Like this doesn't solve the VLM mismatch problem, but at least it solves the bottleneck on inference problem, lets us go a lot faster. Something that I talked about way earlier in this RL section is how we filter out batches with zero advantage. And therefore on the right, what we will often track is the percentage of batches with non-zero advantage. This being between 0.4 and 0.8 shows that we have a lot of problems where the model will always get it wrong or always get it right. This variation in batch size adds numerical stability because generally just the loss steps will change a lot, and reduced batch size is a huge loss in training signal and just kind of efficiency to our training. We want all of our training steps to be very valuable. So this is where we came in with this active sampling idea, which is like, how can we get all our batches to be filled without needing to use a ton more GPUs on inference? Like, we don't want to have to scale up our inference GPUs by 2x in order to get from a half batch size to a 1 batch size. So what we're doing here over time is we're pulling completions from our generation GPUs to our train GPUs. And if some of these have all the answers wrong, so like this top case where all the completions get a wrong answer, what would happen is the train GPUs would have it would get filtered out by the GRPO gradient. Our Olmo RL approach, where we're not using these samples, would remove it. So then we could end up with batch sizes that are less than 0. The idea is then our core idea is what if we could make our RL infrastructure slightly more asynchronous and just wait for more completions to come in with non-zero gradient. So previous, our batch size check was just how many samples we got from generation. And next, what we're going to do is add an intermediate step, and our batch size checker for each RL step is our batch is ready to go when we get enough out of this active buffer with non-zero gradients. So we just let our generation GPUs run longer until our batch size is full of prompts with gradient. In practice, we end up throwing out a whole bunch of completions we've run inference on, but this is much more efficient than just statically increasing the number of GPUs for generation to try to just force the throughput through in our filtering by making the batch size bigger or taking more steps. So we can really get a constant batch size of 1. I think if you look at our newest RL runs we're running, they literally all have a full batch all the time, and it is pretty eerie in terms of the loss. The RL loss without this looks very spiky, and the RL loss with it looks completely flat. It almost looks like we need to add learning rate schedules to our RL, like is done with pre-training, now that we added this, and it's something we added recently and we're really still getting used to. At the same time, a big thing with our RL push, where most of this I was talking about infrastructure for long context, is to show that we can do RL in base models, which is known as RL0 in the literature. And our goal here was to show that for researchers, the RL0 on Olmo 3 is much more efficient than Qwen 2.5, which is commonly used for research, because some people see that the Qwen 3 base models are just a bit harder to wrangle for RL. We don't know what's going on there. And here's the thing where we're showing the number of RL steps that we're using versus the DAPO paper. And we show that the Olmo 3 model on this Amy average at 32, or the average score for the val is much better. So we really hope this is convincing people of okay, I can try Olmo. It's not a step back from models we've been using earlier in the year. It's a step forward, and it's fully open, and I can see more in it. The way that we got here is by using RL0 as a feedback loop during mid-training, where we really wanted to see if we could design our base model specifically with RL in mind. It was a bit of a mixed bag where, yes, we were looking at it, but it wasn't clearly causal, where a specific data set in mid-training made the model much better at reasoning. As we got towards a better mid-training reasoning mix, we saw that we could have this kind of response length increase, which is canonical of this RL and base model working. But it's not obvious. I think the best thing to do for mid-training is focus on very high quality data in math and reasoning, especially with these complex, what some might call cognitive behaviors, and quality data, and you just keep amassing it, and your downstream model will be better for RL. We have a lot more work to do here, but it's kind of a fun tidbit that you can see in the paper on how mid-training interfaces with this RL0 research. The final RL runs with this infrastructure, when you go back to this Olmo 3 pipeline with SFT DPO RL, take a very long time. Our 7B runs ran for about 4 days. Our 32B runs ran for almost 3 weeks. We're going to release an updated version soon, where it's just kind of the downstream performance of our 32B model is just going up and up and up. Even at 32B, like where we ran for multiple weeks, you can see things like Amy still look like they're going up. IF eval is still going up, and like our naive average eval is still going up, which is just a very different paradigm in terms of post-training, where previous post-trained models like 2-3 and Olmo 2, we could do the whole recipe in the week. But now we have a huge motivation to increase the learning efficiency and time efficiency of our RL algorithms, because this 21 days is very big proportional to pre-training, which only takes like 45 days. So now we have a lot to do to make our RL faster while still getting this performance. But I think it's a wonderful benchmark for the community that's going to be able to look at all of these. And now we're going to kind of see how we can take Olmo RL to be even faster and more useful to people. This is the pipeline we talked about. I'm going to now transition into what I'm going to say second NeurIPS talk, which was on evaluations, because I've talked about this recipe, and at the end of the day, the only way that we can really believe it and trust it is by having evals that we care about. And I called the title of my eval suite that good researchers obsess with evals, and it's really true. I think whenever I look at the people at AI2, the people I respect the most are almost maniacally obsessed with evals. It's really hard to get around this, where because language modeling can be so weird, it's so hard to trust your own results at times, which feels like a YOLO run showing you something totally unexpected. The eval's confidence needs to be so high, especially when you're comparing to external models, where your eval suite is different than their eval suite, and you always know that that's imperfect. So this part of the talk is really a reflection on that, how hard it is to get evals right, and it is just a kind of never-ending whack-a-mole of pushing away your doubt by going extremely deep into the technical details of what evaluation is doing. So if we start our eval suite, I think like any language model, you're transitioning from what you previously had. I think language modeling is technically so complex that there is so much work to do that you will always take the older thing and evolve it when you can, rather than rebuilding from scratch. In this case, this is a screenshot of the Olmo 2/2-3 eval suite, which utilized COT much less and had a lot more multiple choice answers. And the thing is, like, how do we evolve this to be a reasoning eval that is useful for Olmo 3? What you really do is you end up making a gigantic Google sheet. I think this had about 60 evals in it, and we prune this down to about 20, where you take everything you can possibly want. You want to see if it's implemented, you want to see if it's been reproduced versus the original paper, and then you have to take this gigantic list and prune it down to something that is useful for development, compute efficient, and kind of really trustworthy. And the process to pruning a gigantic list has a lot of things. I think that, for one, what the community is interested in changes over time, and you prune the list based on just relevance to start. Some of the things seem a little wacky, so you don't need them. And then when you're benchmarking, you can benchmark trial versions of your model, and if evaluation is less than 5% or really above like 80%, it's outside the range of concern. Saturation is still a problem in our eval suite. A lot of our evaluations were saturated on our 32B model. And then you want to balance across skills, where our eval suite ended up being a bit math and code heavy, especially with an instruct model, where we were missing out on chat and other stuff like this, where this balance is very hard, because once you prune by the range and how much you trust the eval, you can often have a lot that aren't left. And then also just some evals don't really work, and it's like they just kind of break, and you just kind of like, they just die. You just lose track of them. You're kind of like, there's like, eval maintenance is a big time sink, and it's easy to lose track of. So when you look at our Olmo 3 suite, you can read through these numbers. First, you will see that every single evaluation is COT, and everything is with temperature greater than 0, which is the biggest substantive change to the suite, but it's also a lot more math, code, and puzzle evals. And like choosing a checkpoint ends up being much more nuanced, and I'll comment more on this later when I have the slide on instruct numbers. So the changes I was commenting are that it's like much more challenging. You have COT format with temperature greater than 0. So with those two things, you need to spend a lot of time finding the stable sampling settings where you need answer extraction, you need the right prompt, you need the right temperature across peer models, you need all sorts of things that you didn't need before. And you need the right context length. And this is like way slower in terms of feedback time. I think that each eval run of Olmo 3 will take 10x the GPU hours to a non-reasoning model of the size or even more. So it's just a really big change in how important evals are computationally to doing post-training. For these sorts of things, early in the process of building the eval suite, a student, Yuling Gu, kind of went through all of the sampling parameters. And what we did is we compared the old eval suite, which is Olmo 2, which is much more multiple choice, much more short answer focused, to the new eval suite, which is COT, which is a bit more open-ended, temperature greater than 0 with answer extraction. And then we compare both an instruct model, which is orange, designed for that suite, and a reasoning model, which was the distill from DeepSeek R1 onto the Qwen 1.5B from Qwen 2.5. And here you can kind of see how like the old eval suite favors instruct models, and the new eval suite with open-ended reasoning ends up favoring these reasoning models with higher temperature. And also the reasoning models have higher peak performance. And this, for example, is a sweep over temperature, where we can see kind of that temperature 0.6 is about best for both types of models. And we were trying to create a eval suite that was representative for every type of model, even if it is favoring our think model, which is the most important thing to get out the door in 2025. Here is temperature. And next you can kind of see what percentage of generations exceed certain token lengths. I think in Human Eval Plus was like a completion style eval, which we changed to giving the model time to think and then writing the function. It's just like the tokens used is so much higher in this new format. And what this means is that like on the right, you see that you need to do longer generations in order to saturate the performance. And if you're doing too short of a generation at eval to try to save in time and compute, you just don't have a representative evaluation. We ended up using 32K for all of our evaluations, especially at 32B. That's kind of the max length. That's nice, where like it just starts to be headaches with longer evals, especially if you're going to try to match your RL training length to that higher eval length. And then here's our Olmo 3 instruct numbers. I think that when you see that our eval suite was obviously designed for thinking models, you can see how having so much math, reasoning, and code kind of distorts the instruct model. And we're kind of really wish we had more chat evaluations. Like we had alpaca eval here, but we don't even feel like alpaca eval is super representative, where it's just kind of like too vibesy to measure if the model is really better. And this is the problem with being limited on the evals you have, is that our tooling, centralizing it is so efficient from an operational perspective that it made choosing the checkpoint for these instructs models a bit harder, because there's no longer that we just want to choose the instruct model with the highest average overall, but we're trying to choose a mixture of vibes, a mixture of key evaluations. Like personally, I don't think an instruct model, which is really fast and short to answer, doesn't need to be solving AMY. AMY is kind of an arbitrarily hard math problem, where the instruct model, we want it to be knowledgeable, we want it to be funny, we want it to be very useful and concise in code. So this kind of is a quick summary of where the future work is probably going, but it's like the evaluation suite makes these types of models from the community honestly more slept on, because it's so much easier to get a reasoning model, which way higher evals, but it might not be as useful in every case. I'm going to take a quick break. I'll be back in a second. Okay, I'm back into the gray area where doing evaluation, especially the longer you go in the project, I think if your evaluation is static, you run into this where you feel like you're benchmarking and you don't really know why the numbers are going up, but they start to almost feel unrepresentative because you don't have enough evaluations. I think that AI2 is very careful about decontamination. AI2 does things like we have a development suite and an unseen suite to test generalization on the evaluations, where we're very transparent on this. I think that's really relative to Like Quen gets a bad reputation, but I think they're probably slightly closer to benchmaxing, where they're leaning more into getting benchmark scores while also making a great model. And we just don't really know what is happening at closed labs. Like I think that something like Anthropic, where you look at their announcements where they list so few evaluations, I think they just don't care about benchmarks that much, and they're just trying to make models that are great. But whenever you make an evaluation suite, which is your target for development, and you need a target for development, you're going to be benchmarking against it, and testing generalization in real model performance is extremely hard. So I think that it's kind of inevitable, and there's more reflections of this in my talk. I think, for one, it's like models have very different strengths and weaknesses, so doing an average column is very misleading. What often will be done with the releases, and you'll say your model is better than the peer by looking at the average across evals. In reality, not every eval is equally important or is equally easy to move in fair ways. So taking this average, I felt like, is very misleading, and we stopped doing it for our models. And like, therefore, it's like, it makes the reader look at the evaluations and think about what they care about in order to decide which model is better. And any model where the quote unquote average would be within 1 to 2 points is kind of left to the reader to decide if it works for their task, because these evaluations very rarely map to what the user actually needs. So I'm happy that we moved on from this in our tables, where it's just like we present the information and make the best case we can for our model, but we do not overstate it by trying to do certain numerical tricks. One such reason where this is very needed is because evaluations in general, and especially with reasoning models, can have very high variance because we are sampling with temperature greater than 0. What we did is, for our 32B model, we had 14 different checkpoints, which is a mix of baselines, which you see in the paper, baselines you don't see in the paper, internal final models from each stage, and so on. And we ran each evaluation 3 times on each of these models, and then per eval, we looked at the per model variance. So we have 3 runs. It's a very rough approximation of variance, but we can then average the variance per model across 14. So each of the numbers on the screen are an average of 14 different variances per a certain eval run 3 times. And we can bucket these into pretty clear amounts of variance, where the variance tells us how confident we should be in the number. And really the average standard deviation across each evaluation is about 0.5 points. So that should tell you that if a model is only better by half a point on these evaluations, it's really kind of a coin flip whether or not it is actually better. It's a bit stronger than a coin flip if it's like a standard deviation above is like 60 something percent. It goes to show this. And the most high variance ones are GPQA, Alpaca eval, and IF eval. And then a lot of them are just a bit lower than this. I think that some evaluations like AMY and Live Code Bench have a built-in averaging, where AMY we need to do average at 32 in order to reduce the variance to this kind of 0.5 point. If we don't do averaging, the variance for AMY would be like over 5 points, which is just untenable. I think everybody needs to be running AMY many times in order to get the score. There's also other numerical things that could affect your numbers. If you serve with slightly different kernels, the evaluation scores could change, especially if they're different than what you ran RL in. So the beauty of RL is that you train in what becomes your intended inference server. So hopefully it matches to VLM. We've seen many other issues, but this is kind of a great representation of variance. And not evals are equally easy to hill climb on. I think that intuitively some knowledge evaluations are really hard, like MMLU, but also some reasoning evals like big bench hard are just really hard to move. I think it's not clear why. You just kind of get to this point in your development process a few months in where you're like, all the things we're trying just don't move certain evals. Where at the same time, some evals are just like pretty standard to hill climb on. Instruction following is well responsive to training data, AMY is, and so on. And on the right here is not like a complete representation of this, because it's hard to show what doesn't improve over the base model at all, because it's like SFT instills the formatting as well. But this is the gains from SFT and then into later stages of DPO and RL, where you can see some evals really improve a lot with DPO on RL in this top right corner, but not all of them do. And I think this is the nature of eval suite. When you're in the later stages of your training, you just kind of lose a lot of signal because you end up only moving a few evals and the other ones are mostly noise. And this is why it's like you just feel like you're kind of pushing up a partial tree and you're kind of taking, you only have so much you can do. Another really crucial thing is that evaluation of models today should be thought of as per token response in the question, and most of what we see is just the highest scores. So you can make another Pareto front, which is the eval average score and the reasoning length per these evals. And what you want to do is you want to have a model that is the smartest while using the fewest tokens. So the ideal would be the top left here, and you can see that Quen does a very good job on benchmarks, kind of hitting this frontier, and this is something that I want to work on, and I think more people should understand how hard it is to move on this frontier, and we could plot like an RL run and see if it's changing, if it's just going straight up, if it's going up and to the right, up and to the left. But this is something that I'll revisit as a kind of future work for evals. And also evals are very expensive. These are kind of summarized bins of, we have compute tracking workspaces where different jobs are run in different areas and they monitor compute. When we're developing our reasoning RL and SFT recipe, evaluations accounted for about 20% of the compute. I think our eval infrastructure is far from perfect. We're doing a big refactor to make this more efficient. But this goes to show that if we were using 500 GPUs concurrently for RL research, like 100 of those would be going to evals, which is a very big fixed cost over the training runs that are nominally showing you the signal. So here between June and December, this would be hundreds of thousands of H100 hours for evals, and you can figure out how many training runs you think that is from there. Well, our final like 32B post-training and hyperparameter sweeps and baseline evals is much higher, where you can use well more GPU hours, but it's like evals are really a substantial thing. I think they're also a substantial factor in time, where you can have training runs that take 12 hours, but running the evaluations takes 4 to 8 hours, depending on the urgency and if you have the GPUs sitting around for them. And this just makes it like, so evals is definitely a center of attention and will often be running the full training cluster on evals. So we have a section in the new version of the paper where we talk about training time, and it's like we use 1,000 GPUs. There are many times in the final model creation process where we have 1024 GPUs all to evals because we are time bucketed on our next checkpoint decision until we have this data, which is something that is often not priced in like compute time and model cost, which is often based just on like pre-training time, which is not kind of a fair accounting. And while I say this, and while I say things that it's like evals are hard and we lose some and like they're very expensive, we still need a lot more evals because we are so good at hill climbing. I think when you have a good scientific rigorous culture, you can hill climb in ways that are not cheating. So I think very highly of AI2's ability to hill climb in fair ways on benchmarks, and we're very good at it. We're good at making the numbers go up. It's also thrilling, but like without having more evals, you're not seeing if you're making trade-offs, and you're not seeing if you're like tanking a long tail performance where you need to pass it by hill climbing so much. And it's like, I think it feels like we don't have the evals that we need to make robust models that people enjoy and that we enjoy. I think the difference between models that evaluate higher on math and reasoning is very hard for me to understand. And we need just a longer tail of evals that's more representative, and especially evals that we can hill claim on, or we have kind of a dynamic range on after post-training or after pre-training. And it's especially things like alpaca eval and chat, where we don't have many evals that we intuitively agree with. And we're very ready to take a model with lower alpaca eval because we often felt like it was better to use, even though we're not really incentivized to do so in terms of the external environment. So I would encourage people to make narrow evals that can be just tens of prompts in an interesting area where people are using models today. And we really need to grow this list from like 15 to 20 to 40 to 50 of evals for any model in the future. And I think our pre-training team has done a bit better on this, but we just need people to be making more evals. And this is a high impact path, I think, especially in academia. So the two things on evaluation that I think is crucial is, one, I want to make evaluation more efficient. This involves better methods for understanding which prompts are important in evals. So some evals are particularly expensive, and you have things like Math 500 to kind of approximate the important samples to run in there. And then also just making models more compute efficient and learning how to do so. And this boundary between understanding what we're hill climbing on by spending less compute on evals, and then also enabling us to create models that spend less compute to get the same performance. Here's a summary of the kind of reflections I included in this talk, where benchmaxing is inevitable to some degree. I don't think naive averaging is a fair way to compare close models, and then reasoning models end up being really high variance, computationally expensive, and whenever you're doing a project like this, you end up with a initial set of 10 to 20 evals, and you're probably really hill climbing on about half of those in post-training, even though you need the other half to show the representation of your model to the community. So things like PopQA, which is a knowledge benchmark, we need to show the community these numbers, but we don't feel like we have any intervention in post-training to actually budget. So if we go back to the start, this is the story that we've told of these Olmo 3 models that hopefully you believe are very solid for doing RL research and are some of the best fully open models we've ever released. We're excited that people are starting to consider using them in products. They've been on Open Router, and people have been generating billions of Olmo tokens into the world. We still have a lot of work to do, but it's a very fun project and kind of gives us a great platform to hopefully do more interesting things in 2026. So when I say what's next, I think scaling RL has been on my mind. I talked about our 3-week RL runs, so some of that niche has been fixed, but also we need to design our RL and post-training approach for bigger models that can do more interesting behaviors. I think I want to have like a local coding agent with Olmo, or a search agent, or like a data analysis agent, and things that are actually more useful because it'll be easier for me to test and dog feed it in my everyday life. So that seems that we're ready for another RL infrastructure challenge on tool use for more agentic models. I think the RL infrastructure challenge will also come with mixture of expert models, which we obviously want to do, but it's clear that we can push this further, and that's what we want to do. This is a huge team effort. I think Olmo is really a group that is dedicated to this goal of like scientifically rigorous and open and kind of these loving, fun artifacts that we put out. So I appreciate greatly working with this group. You can see the links to the models and the data sets. I'll release these slides, obviously, and please ask questions. We'd love to learn how you're using the models and tell us what we need to improve, because that's how we get better. People tell us that's not good enough, and we want to fix it. So thanks for listening. This was a long talk, but I think it covered a lot of great material, and I hope you have a great day and holiday break. Peace.